Video of a series where I'm trying to summarize how the local volume mapper data analysis pipeline works. So this is just an introduction, correspond to a presentation I did in Heidelberg in the collaboration meeting in May 2025. I want to highlight that this is a collaborative effort. So there are people deeply involved, like Alfredo Mejia and Eduardo Lacerda, that were based on the development of this, very deeply involved in the development of this tool. So it's not only myself and other people that have contributed with feedback, and I hope there are more feedback hereafter. So basically, what is the data analysis pipeline and what is its aim, and what is the goals of this code? Well, the goal of this code is to analyze automatically the spectra provided by the local volume mapper once that they are reduced by the data reduction pipeline. So this is important to remind because later on in a second video, I will present what's the format that is delivered by now by the data reduction pipeline, how to read it and how to visualize as a first step before analyzing that. Visual analysis is something that is also important in this context. Its aim is to decouple the emission lines from the stellar component. That's one of the main goals of the tool. Provide with the observational and physical at a certain level parameters of both components, both the stellar component and the emission lines. Deliver the data products in a friendly, I hope, and easy way to use it. There are tools included in the DAP scripts and notebooks. They just focus on how to use the outputs produced by the DAP and how to visualize and to use scientifically. Provide with user-friendly tools to exploit these data products, as I explained before, being easily to distribute and maintain. And the DAP is deeply based on the PyFit3D package. That is a package for fitting stellar populations and underlying continuum emission and emission lines. And all these algorithms you can find in this location that you can download. But actually, when you install the DAP, is installed in a version of the PyFit3D. So it's you don't need to deal with the Adobe installation, as we will explain in another lecture here. So one of the challenges of this tool is that the spatial resolution that we are working, the physical spatial resolution of the local volume mapper data is not fixed, depending, since we are inside the main target that we are observing, that is the Milky Way. There are objects that we are observing that are nearby, and therefore to our projected sampling, the fibers of the around 30 seconds of the local volume mapper. At the objects that are more nearby, we resolve them to scales of around a few parsecs. But when the objects are more far away, we are observing them with a resolution of 100 parsecs. And for the galaxies in the local volume, we can even reach worse, more coarse resolutions. That basically means that we have to deal with the analysis of the ISM and the stellar component in particular under very different circumstances in which we may have inside one aperture just a single star or a very few of them, or hundreds of stars or thousands of them. So this is a patterning situation that is different of what we were dealing when we're using integral field spectroscopy in a classical way that are for extragalactic astronomy. I mean, where basically we have enough stars in the single aperture to apply the synthetic stellar population principles. In here, we have to depart from that. So what we have done is to create a different way to represent the stellar continuum, and we fit basically individual spectra that are representative of a certain type of stars, But instead of using the typical approach where we have a library of stars with a stellar spectra that are characterizing a certain physical condition. I mean, physical parameters like the temperature, the gravity, the abundance, and the alpha enhancement. Instead of having that, we create a new concept that is resolved or partially resolved stellar populations that are spectra that are representative of a group of stars that they are indistinguishable in the parameter space. I mean, basically in the solar signal parameter space, that is basically the spectra. So they have the same spectra, but they may have similar or different physical properties. Since they are undistinguishable, therefore these RCPs, instead of having a particular value in the parameter space, have a probability distribution function that is if it has only one peak, then it's very similar to having tagging just a particular star, but it may be distributed along a very broad range of parameters, and that basically means that the same spectra correspond to very different may correspond to very difficult physical properties. And that is translated in a PDF in the parameter space that we are propagating. So we acknowledge the fact that we have the inerrancies. We are not unable to separate between certain stellar types, and we propagate that the inerrancies through the analysis. So how we do that? Well, we start with a stellar library. So far, we're using the MASTAR stellar library, tagged by the COSHA library created by Alfredo Mejia. And once we have this tagging, we try to sample stars through all the physical parameter space in a more or less homogeneous way. And we coadd all these stars that have very similar physical properties within the errors. This reduce the number of stars from several thousands, like 30,000, to coadding the corresponding spectra to about 1,000 and less than 2,000 characteristics stellar spectra. And from there, we make an analysis of clustering in the parameter, in the observational parameter space in the spectra. So those stars that have an spectra, as I said before, that cannot be distinguished, they are glued together and create an RCP, and their parameters are sampled in the physical parameters are sampled in this PDF that are included. So when you decompose the LVM data or any data indeed with this template, at the end you have a set of weights that correspond to each of the RCPs, and applying these weights to the PDF, you will have a probability distribution function in the physical parameter space that will correspond to the population of stars that you are sampling. Why we do this approach? As I said before, you cannot use the classical approach. Sorry, I have to jump to another slide that is at the end. So this is the situation that we are dealing with. That's a case example of the data we took with Manga on IC342. In this particular galaxy, at the distance that it is a local volume galaxy actually. One single fiber, or one single resolution element of Manga correspond to 40 parsecs. So this is one of the situations that we will encountering with, or we are encountering the local volume mapper. And one single point of Manga correspond to around 1 kiloparsec. That is the situation in which we usually have enough stars to apply a stellar synthesis method. That is what we were using when we were using PPFX and Starlight or PyPy3D or tools like that. However, when you don't have enough stars to sample the complete IMF, you cannot trust on the stellar population synthesis. You cannot assume that you are sampling an entire population, and you need to apply a method like the one we are using, and that's what is simplified in the upper panel, where basically we are showing what happened when you have either individual stars or just a group with a handful of stars that could be between 1 and thousands of them. So using RCCPs, you acknowledge the lack of a certain information, and you acknowledge the degeneracy, you propagate it with PDF, but at the same time, you can run the code in a consistent, physically consistent way from having one single star to having thousands of millions of stars. And that's just to remind that in the basic difference between our single star population and an ICP, single star population is created assuming a complete coverage of the IMF, enough stars 10 to the 4, 10 to the 5 stars in the aperture, assuming a certain distribution in the physical parameter space that is covering a certain isochron, because an SCP, you have to remind, is a spectra that is characteristic, created synthetically, that it's a characteristic of a certain population created with a certain metal content that has evolved at a certain time from it was formed in a single burst. So therefore, at a certain time, they are distributed following an isochron. And in the case of the local volume mapper, we may have stars that were formed at the same time because they are at the same distance, stars that were formed at different time because they are at another distance, and therefore we cannot fit that so easily with an isochron. And of course, we don't sample the IMF. We have one single star, or have some kind of a stochastic sample of the IMF, or a totally incomplete one, just a handful of them, and therefore the spectrum we observe is not represented by an SCP. And of course, at the end, for an SCP, you need an stellar library, like MassStar, for instance, that you are attaching, or you are associating a certain distribution along the isochrons with a certain numbering given by the mass function, because the IMF evolves in the mass function along the time. The more massive stars die before, and they disappear, and the distribution is starting to get truncated as you evolve in time. So you integrate the mass, the transform to light function for across a distribution in a certain isochron, and associate each point in the isochron to a certain star in the stellar library. And when you sum all these, you create an SCCP that it's what we then fit to integrate the spectra. Again, if you have just one single star or a very few number of stars, you may not sample IMF. You are not going to sample IMF. You cannot trace all the location in the isochron because you will have one star here and one star here, and therefore you can go through the stellar library and fit individual ones. But again, if you have the degeneracies, fitting individual ones is not going to help a lot, because you may have a bimodal distribution in the physical parameter space, and it may be unreal. So this is the basic difference between an SCP and a RCP. This forces us to change the code somehow to deal with these probability distribution functions. Okay. So let's go back to here. So now, and this is the distribution of one of the RCPs that we are in the spectra of the RCPs that we distribute with the code. It's a different repository, and other lectures I will indicate how to download these templates. And just to show you some samples, this is a number in the RCP index, so it's nothing apart from a tagging and an ID. In black is the actual spectra of this RCP, and in orange is 1 sigma of the different stars that have entered in the generation of this RCP. So as you can see, there are some of them where there is a very little difference between the average and the full distribution. In other cases, there is a wide range of observational parameters. This is propagated in the error somehow. And just to show you an example of how the PDF look in the physical parameter space. This is for 3 of the stars that are shown here, and this is a young, this is representative of a young stereotype population, and somehow a bit more metal poor. And this is a 14, it correspond to this PDF here, and the temperature is the range of temperature is quite narrow, but the range of gravities is much larger, and the range of metallicities in the metallicity distribution, in this distribution metallicity versus alpha enhancement is quite wide. This is 35. If 35 is somewhere 38, sorry, in here. It's a more average temperature, and again, temperature is very narrow. The gravity is covers a wider range, and again, a wider range in abundances. And this is in the case of this 47. This is a cooler star, and you can see that its temperature is very well defined. But in the case of gravity, it's degenerated, so that I have no single peak in the PDF. That basically means that the different stars in here share the same temperature but very different gravities, and they are undistinguishable, and that stars that enter in this RCP. Curiously, the distribution in abundances it's quite different, and it's very narrow both in the iron and the alpha enhancement. So this is how we decompose the stellar in the ingredients in which we decompose the stellar component. Okay, so the LVMDAP, what you may find in the GitHub repository when you install it. In another lecture, I will teach you how to do so. It's a set of scripts. This is the LVM DAP conf. It's the main script that runs automatically through a local volume mapper reuse frame corresponding to a certain tile or group of tiles. It's what is described in the article. Then we have the LVMDAP sim, that is a tool that uses the output of a certain certain analysis to create ad hoc simulations that you can run again to test what are the limitations of the method for your particular data set. We have a wide range in the data in the local volume mapper in the current reduction have very different degrees of qualities depending of which target you are sampling, the sky subtraction, particularities of the night, and so on. So I strongly recommend that you repeat the simulations that are included in the article when you are dealing in particular with low intensity stellar components or low intensity emission lines to understand with these ad hoc simulations what you can trust and what you cannot trust. There are new tools like this LVMDAP Gen Out mod. It's to generate output of the model. So far, when we fit with the we fit with the DAP, the local volume mapper data, we are not storing a model of each of the components that have been decomposed automatically, but you can set a parameter to store it if you want to run yourself. But you can a posteriori generate this model, and this is the main reason not storing that is storing capacity, but maybe this is going to change rather soon. The fitting is controlled by a YAML file that I think I'm going to devote a video just to explain it, because they have a lot of parameters and many of them you don't need to touch. We distribute the samples of how to run that, and in some cases, again, because of the wide range of difference between the different data produced by the data reduction pipeline, you may require to tune these YARN files to improve the fitting or for your particular data set. To facilitate understanding of the code and for many people that are like me, visual kind of person, I create a notebook that is basically replicate what the LVMDAP conf script does in a notebook version, so you can run the script in bunches and cells, and you can stop and visualize the results or change something, came back, typical thing that you do with a notebook. It's a bit slower, but it's interesting. Of course, you have also a notebook that for generating the model spectra. We have a visualizer of the data reduction pipeline frames. I will devote the video just to this one because and maybe the first one because it's important that the people understand the format of what we deliver and how you can read it and how you can visualize without the need of making interpolations and creating cubes or things like that. Remember that the local volume mapper data are sampling the object in the quasi-continuous way, but in a non-regular grid. So fibers are distributed in a hexagonal pattern, and there are, of course, is a fiber bundle. So even we have an hexagon lens array in front of the IFU. You have holes in between one fiber and another. You don't sample 100% of the field of view. There are some tools for reading and plotting the results of the DAP. The DAP produce a result in a certain format that I will explain later. And those tools facilitate the people to read and plot and create science results. There is a tool for plotting the model that is generated here. This very long name, plot fitting output spectra, is self-consistent name. That facilitates the visualization of the fitting. And finally, there is a tool for plotting the probability distribution functions that are generated by the analysis with the RCPs. We need to remind that so far, by now, the weight, more weight in the local volume mapper is in the mission lines, but we provide with these tools because we hope that we can also make analysis of stellar populations with this data. The details of what the DAP does. Let's see if I can put that in here, for instance. It's in the article that present the code. I'm just going to go very briefly in here on that because it's not the main goal of this talk. The main goal is to learn how to use these tools. Basically, first we make an analysis of what we name the nonlinear components, basically to recover the velocity dispersion, the dust attenuation. And this is done fitting the stellar continuum, masking the set of emission lines that, of course, are defined in the YARN file with a subset of the RCPs. The reason for that is to avoid degeneracies as much as possible and speed up the process. This has been tested with simulations, so we know that they are reliable. And the output of this analysis is basically the systemic velocity, the velocity dispersion, and the dust attenuation. In this process, we assume that all RCPs share the same dust attenuation in a screen, like a screen dust approach, the same velocity dispersion and the same systemic velocity. And of course, this is something to discuss for future developments, but so far it's in that way. When we are satisfied by this fitting, we create the first model of the underlying stellar population we subtract this model and we create a gas pure version of the emission lines and with the noise. And in there, we fit a set of emission lines that you define in the YAML file with a parametric function that is a Gaussian function for each emission line. And there's a discussion if the Gaussian is the best approach or several Gaussians, different velocity components, and so on. This is something that we need to implement sooner or later. And so these there are groups of emission lines that we name systems that are emission lines that are nearby in the well-length range. And in general, we only fit the strongest emission lines with this technique. We take this gas pure plus noise spectra, the one that we derive from subtracting the standardized population, and we fit with Gaussian functions using a procedure that first make a brute exploration of the parameters and then refines with the LVMDAP method, provide with the intensity, the velocity dispersion, and the intensity, the velocity dispersion, and the velocity of each emission line. And once you have these emission lines fitted, you can subtract it to the original spectra. So you create the inverse of what you had before, and a stellar component spectra with just the stellar component subtracting the strongest emission lines. And for those for this stellar component, we fit with the full library of resolve stellar population templates, and this can be it. From here, you fix the non-linear parameters, the velocity dispersion, the dust attenuation, and you apply these parameters to the template, and you fit the model, and you recover the weights of each RCCP, and that weights can be used to generate the PDFs. Once you have that model, you can iterate, subtract this model again to the original spectra and fit the emission lines and iterate. Normally, this converts in 1 or 2 iterations, so this is not really required, but you can do it. Once you have the best model of the stellar component, this is an important note here. Nebular continuum is still not included in here, and we need to figure out how to include that. Just to make a note, you subtract that, and for the residual spectra, that's similar to the one that you enter in here, but they're more refined. We make a non-parametric analysis of a wide large number of emission lines, both strong and faint. Of the order of 200 emission lines are analyzed in this process. This analysis is based in a weighted moment analysis. It's pretty fast and quite reliable. There are some emission lines that are blended that you may present problems with this analysis. And having that analysis, we also perform a second fitting with the same, for consistency, with the same of a larger number of emission lines using the parametric fitting and using as input and as guess the results of the non-parametric fitting. So at the end, we have 3 analyses of the emission lines so far. The one that is produced in this loop, the one that is parametric, the one that is produced in this part that is a non-parametric moment analysis, weighted moment analysis, and again an analysis using the same spectra, subtracted the best stellar continuum, using again the parametric properties and as guess the values of the non-parametric ones. So this is basically how it works. It's not very different from many other loops in this kind of fitting that you may find in literature for other IFU data, with the peculiarities that I indicated before, the recipes and the different loops in the analysis of the emission lines. We still need to decide. So far, we distribute all of them, but we need to decide which one maybe we are going to distribute at the end. Maybe so far, I prefer to distribute all of them and see later on what's the best option, or left the user to decide that. Okay, so this is an example of the non-parametric fitting. I'm not going to go through that. It's a brute exploration of the velocity dispersion, and dust attenuation. And this is the chi-square maps where it's defined. There are two loops. One is some kind of a Markov chain, a pseudo Markov chain, where you have a brute sampling and then a sampling of around the minimum to improve the values of the three parameters. So far, this is fit with 12 RCPs, but again, this is for the distribution that we do internally, but we need to decide for the distribution that we are going to distribute everywhere, which is going to be the final number, and everyone can tune the jam file and fit whatever they prefer. This is the first fit with RCPs fitting, including the emission lines. And this is the kind of plot that you generate for a particular science case. This is the full spectra. These are some details on strong and not so strong emission lines, some details on certain Wellen range, just to visualize the fitting. And in dark blue is lines that has been fitted with the Gaussian parametric fitting. And in here, in these marks in here, well, these marks in here show all the emission lines that are analyzed using the non-parametric fitting. Okay, this is another example of how the fitting works when we have some issues sometimes when there are negative coefficients in the composition, and what the iteration does, and this is it is not a RCP, it's an RCP. The tool works in the following way, and this is the principle of how Pi-3D works. It allows the composition using positive and negative weights in the composition when RCPs have the composition with a value of the coefficient that is negative. This RCP is removed from the library and the library is fit again. And this is repeat several times using Monte Carlo iteration, and this Monte Carlo iteration, what it does is when you create a new version of the spectra, adding the noise, the composition you get is different, and for those that before were negative, now they are positive, and they are weighted in a different way. And since you make the average of all the different decompositions, and you have at the end you have a wider coverage with taking into account the degeneracies. That was explained in the Pi-3D articles. And of course, you have the values of the weight in the decomposition and the errors, and some kind of again a PDF in the parameter space, and that's propagated to the PDF to generate the final PDF in the case of the stellar population. Well, I'm going to skip those. There are details. This is how the fitting of the parametric, how the fitting of the strong line works with the parametric modeling. There's oxygen 2, different Balmer lines, oxygen 3. This is nitrogen and H alpha, sulfur, sulfur 2, the sulfur 3 in the infrared. And you can see in light blue is the what we name the stellar residual, I mean, or the gas pool when you subtract the stellar population and you have just the emission lines. And in dark blue is the fitting with the Gaussian function. And when there are blendings, you always may have some issues, but in general, the fitting is quite good. And this is the result of the analysis in the non-parametric. Since it's non-parametric, there is no model actually that you fit, it's a derivation using a weighted moment. But you can assume that if we assume later there is a Gaussian, that in principle it may not be, if you have asymmetries, it may not be a Gaussian. You can create a Gaussian function that have the same parameters as the one that you recover with the non-parametric function. And then you can compare the results. And as you can see, it's not perfect matching because lines may not be a Gaussian. And if there are differences in the non-parametric and the parametric, especially in the velocity dispersion and in the flux, but especially in the velocity dispersion and the velocity, this may be an indication that you have multiple components in the emission lines. And it's something that we need to investigate. We have not made simulations about that, but we can do it using the simulator that I said you before. Anyway, we provide that, and we provide also with a tool to generate this model in case of people want to compare and visualize the results. Of course, we have run a lot of extensive tests of how we recover the parameters for single stars. This is in the left side. In the case that you are sampling, in the aperture you have, the spectra is dominated by a single star, and this is how we recover the parameters. We perturb them star library, and we run with different levels of noise, and we fit and we recover with the DAP, and that's usual results that in general you find that the temperature is better recovered than any other parameter. Gravity is recovered well only in certain range of parameters. The metallicity, the iron abundance, it's recovered quite okay, and then you have issues with alpha enhancement. When you mix stars randomly between 5 and 125 stars, and then the situation is not that nice, and it's not completely right to make this comparison here, because we are all the time talking that what we get is a PDF, and this is marginalized. That is the average. So again, we have a PDF, and we are assigning at the end an average temperature. So it's not comparing apples with apples. Well, it's comparing apples with apples because we do that in both axes. But how the PDF chain, how the average is representative for population when the distribution is not centralized or Gaussian, then it's something debatable, no? But anyway, it's not a total disaster. We find we have some bias. We're surprising, but they are in there, and we don't know certainly what's the source of that. But at least when something is metal rich, we recover metal rich. With metal poor, we recover metal poor. And temperature we recover somehow. So it's not perfect, but it's what we have. For the emission lines, the situation is better. For the flux and the equivalent width, they are recovered pretty well, both in the non-parametric and the parametric values. And the velocity, it's recovered. This is including lines of a very wide range of signal to noises, and when you have good signal to noise, you recover well all the parameters. When the signal to noise start to go down, then this does not affect only the flux, it affects also the velocity and the velocity dispersion. That's a well-known thing. And this is a comparison between the parametric and the non-parametric fits for simulation, for simulations created with a local volume mapper simulator. That's another tool that corresponds to other people to explain. And here it's the comparison we get, consistency between the derivation of the parametric and the non-parametric analysis. When we do an analysis on a certain target that have a very good signal to noise. So this is just to highlight the possible systematics, so that's it's not affected by signal to noise issues here. And that's Orion. And Orion, of course, we have it's a monster, so we have a very high intensity, and you recovered quite well the parameters. Okay, again, I have to highlight that even for single stars, the program does not recover only a single value of the physical parameters. What it recovers is a PDF. So this is the distribution functions for the entire RCCP that is fit, and the logarithm versus temperature, gravity versus temperature, alpha enhancement versus temperature, alpha enhancement versus metallicity, and gravity versus metallicity. These two projections in general people don't use them, but okay, I prefer to show all of them. And normally this is shown inverted, another detail that is not that relevant. So in black and gray is the distribution of the full RCCP that has been fit in this particular analysis. In blue is the value of the individual star that has been perturbed and fitted from the master library. And in light red, it's the PDF recovered by the DAP. Remember that the DAP recovers a PDF. So if you marginalize that, the gravity and temperature are recovered quite well. Of course, gravity is recovered well, but the abundance is not recovered quite well. And alpha enhancement has also a wide range of values for this particular star. What I want to highlight here is that you don't have a single value of the observed parameter space. You have, sorry, in the physical parameter space, you have a PDF. That's important to keep in mind. Well, there's some examples that are shown in the article of a simulation of real data. Sorry, perturb ad hoc, and this is the input values. We perturb them and we fit again, and this is the output, and this is the spectra integrated and how the emission lines are fitted. And this is a simulation created using the LVM data simulator, using well-known physical properties. It's a nebula that it's ionized by a star or a single or a group of stars, young stars, and that's the typical H2 region. And in here you have another component that you can see in here. And this is the input, and that's the output. And again, this compare, and this is in the article. You can check the details in there. And of course, apart from the emission line fluxes, we also recover the velocities and the velocity dispersion for the different emission lines. When you have good signal, I mean, you have good signal to noise, then you recover well. As I said before, when you have low signal to noise, then you start to depart, especially in the velocity and the velocity dispersion. Okay. Once you run the DAP, and we will show you in another lecture how to install it and how to run it, what the DAP produces and what is going to be delivered at the, somehow have this data format. For each tile or each run of the DAP, you have a DAP file. It's a fits file with certain extensions. The first extension is the primary header, that is basically the header of the local volume mapper reduced frame produced by the data reduction pipeline. So you can trace back to which frame you have been analyzed and what's all the details of the observational details and of that frame. Then you have a first extension that is the position table that's also inherited from the reduction. It's only for the science fibers, so sky and calibration fibers and so on. They have been wiped out. Then we have a third extension that is RCP table that comprise the average parameters derived from the analysis of the stellar population. So the average temperature marginalized through the PDF, the log G, the iron, alpha enhancement, and the non-linear parameters, the dust attenuation, the velocity dispersion. We have another extension that have the weights of the decomposition of the stellar population, so the coefficients. So for each spectra, you have a table with the weights that you need to multiply for the RCP library to create the model, taking into account the non-parametric, non-linear parameters, that's the noise, velocity versus dispersion. Then we have the properties of the emission lines fitted with Gaussian models, the parametric PME lines, that are the ones that produce in the first loop that I showed you before. Let's see which one in this loop here. Okay, remember to have one parametric, one non-parametric, and a second parametric. Okay, so this is the one parametric, this is the non-parametric, and they are divided in 3 extensions because there is a limitation in fits tables to less than 1,000 columns. I need to divide it in the 3 range: the blue, the red, and the infrared of that correspond to the 3 arms of our spectrograph. These are the non-parametric property, the properties of the emission lines derived from the non-parametric analysis: flux, velocity versus dispersion, equivalent width H alpha, and the errors, again generated with a Monte Carlo. And this is the second the result of the second iteration using a parametric analysis for the strong emission lines. And finally, there is a final extension that is named info, where it's all the entries in the YAML file that you use for fitting, and that's important to trace back what have you fit, with which template, with which input parameter, with each range, everything. So you want to repeat the fitting or create a model using that fit. Okay, so well, apart from that, the DAP analysis can generate a model that, as I told you, is switch off in the current run through all the data set because of space. But with this LVM data gem model, you can create that model, and this model is large because it contains the original spectra, the model of the stellar population. It's basically it has the format of a cube, in which you have in the Z, you have X and Y. X is the wavelength range, Y is each of these models, and Z correspond to each of the analyzed spectra. So for each analyzed spectra, you have a slice that contain the following information. It's a row stack spectra in each slice that contains the original spectra in the first row. In the second row is the best fitted stellar population model. In the third is stellar population plus the non-parametric models of the emission lines. The third is the gas pure. So basically it's 0, -1, removing possible deviations of low order between these two values. The fourth, the residual subtraction of the model of channel 2. So basically the sum of the adding of the emission lines and the adding of the stellar population and the emission lines to channel 0, so it could be like a residual. 5 is stellar pure, so we subtract the emission lines and we obtain a spectra without the emission lines. 6 is the emission line model derived from the non-parametric analysis. And 7 is the emission lines derived from the second Gaussian fitting. And 8 is the stellar population model plus the emission lines in 7. So in 2 is the stellar population plus the non-parametric analysis of the emission lines. In 7 is the stellar population plus the emission lines. And no, sorry. In 8 is the sum of the stellar population plus the emission lines derived with Gaussian fitting in the second fit. So 8 and two are similar, but one is created using the non-parametric fitting of the emission lines and all the parametric fitting of the emission lines. So, and all this is stored for each spectra that you analyze. As you can imagine, the file is huge, and that's the reason why we don't store so far, but you can generate later. So I'm going to stop here because that corresponds to a description of all the different notebooks, and that I think I'm going to one by one in different video. This was just a brief introduction. These are different notebooks that have been included. I think this is it's good to have it for other talks. And I want to point to this LMBV's created by Ban. This is the current analysis we have for the DAP on the DRP, and this is going to be very quickly outdated with the new DRP. So thanks. That's the first of the videos.